pH curve, when you increase the magnetic field intensity, the magnetic flux density is going to be increased, and your material, any material, is start conducting from 0 point to the A point. Okay, when it reaches at point A, it saturates, and again it discharge from A point to B, then C, then D. Okay. Again, it will charge from this point and reaches at point A. So this process continuously going on. Okay. So how this process comes under this hysteresis loss? As you can see, there are magnetic materials are present in this whole process. Okay. Due to this reversal of flux, what happened that there is a Lenz law. So we have to use this reversal of flux using this Lenz law. Okay. So when this reversal of flux happen, we need more power. Okay. We need more power to reverse the molecular magnets. Okay. So when you use more power to reverse this molecular magnets, then this power is going to be dissipated. Okay. So when this power is going to be dissipated in the form of heat, it is called a hysteresis loss. Write in chat box. Have you understood this hysteresis loss? How this is happening? Write in chat box. Okay. So now to minimize this hysteresis loss, we have to use this silicon steel. Okay, so when you use this silicon steel, then this loss of power is minimum at that point. Okay. Next, come to this eddy current loss. What is this eddy current loss? As you can see, there is a flux linkage in between these primary and secondary winding. Okay. So when your primary and secondary binding is going to be linked with this flux, then this eddy current will be generated. So how this eddy current loss will generate? When you give the power, okay, it will be dissipated in the form of heat, okay, and this eddy current will be generated. So these two, hysteresis loss and eddy current loss, these two losses occurs due to the heat. Okay. Understood? Write in chat box. Write in chat box. Okay. Now come to this core or iron loss. What is this core and iron loss? As you can see, we have used AC supply and we have applied that AC supply toward the primary side, and this flux is generated and linked with the secondary side. So we have used primary side as this core. What is core? There is a primary core and there is a secondary core. Okay, so this is a core, primary side and secondary side. What is this iron loss? Inside this there is a material, okay, iron material. This is called iron material. Okay, so when any loss occur between this primary side of core and with the help of this iron material, so that loss will be called as core or iron loss. Understood? Write in chat box. Understood? Understood? Okay, now come to this copper loss. What is this copper loss? When this is a material and you have placed binding, so that bindings are made up of this copper. So these primary binding and the secondary binding are made up of this copper. Okay. So when any loss occur in between these bindings, this is called as copper loss. Okay. So how this loss can be calculated? In the primary side, you can calculate this loss using I1 square into R. Why we are using this I1 square R? You can calculate this using the formula. Okay, so how this power is going to be dissipated? I square R. This is the formula for your primary side. Whereas in the secondary side, you can use I2 current and the resistance across this winding is R. Okay. So in the primary and the secondary winding, due to the ohmic resistance, this copper loss will be generated. Understood how this copper loss is going to be generated? Write in chat box. Any doubt till now about these losses? Understood very well. Write in chat box. Understood? Okay. So now let's come to the next point, how to calculate the efficiency of the transformer. So efficiency can be calculated using output power divided by the input power. Okay, so how to calculate this output power? So this power can be calculated using voltage multiplication with the current with the angle, okay, some angle. So V2 into I2 into cos of phi. Okay, this is called output power. And this input power is going to be calculated using output power plus copper losses plus this iron losses. Okay, so we have calculated this output power, so we put this output power as it is, and this iron losses and copper losses. So how to calculate this iron losses? You can use this pi, and pi is equal to this I2 square into R. Okay, so you have to put these values right here and you have to solve this equation and we have to calculate the value for this efficiency. Okay, so this efficiency is equal to V2 into cos phi divided by V2 into cos of phi 2. Now we are using this phi 2. Phi 2 is in the flux generated in the secondary side. Okay, that's why we are taking this as a phi 2. Have you understood this? Any doubt till now how to calculate the efficiency and what are the different losses in your transformer? Write in chat box. Understood? Can we move further? Sir, efficiency, can you repeat the formula? Okay. So as you can see right here, we have taken the output power divided by the input power. Okay, so how to calculate this output power? So we have to use the voltage across output. Let's take a look right here. Here is our metal case. There is binding. Okay, primary side. This is the secondary side binding. So in the primary side, we apply the voltage V1. This is the current I1. Okay. In the secondary side, we provide the voltage V2. We provide the current I2. Okay. So how to calculate this power? Power is V2 into I2 into cos of phi. Okay. So we have to calculate the output in the secondary side. We have to calculate the output in the secondary side. Okay. So secondary side, what is the voltage? Voltage is V2. What is the current? I2. And what is the angle right here? Cos of phi. Okay. So input power we have to calculate. How to calculate this input power? It is equal to output power plus copper losses. So output power is represented as it is, as we have represented in numerator. And what is this copper loss? Copper loss is this one. Okay. So how to calculate this copper loss? First is iron loss, then is copper loss. So in the numerator, you have to make this equation as I2 common. We are going to eliminate this I2 current. Okay. So while making this I2 as a common in all the terms, we have to divide this pi. Pi means this power is iron is right here. This is copper losses. This is a copper loss. Pi is a iron loss. Okay. We have to divide it by I2. Okay. So then we have to put the value for this copper loss. What is the copper loss right here? Copper loss is I took a square into R divided by I2. So from this I2, this I2 is cancelled out. So what is present in the denominator? It is I2 into R. Okay. So have you understood this? How we have calculated this efficiency? Understood? Pankaj, understood? Okay. So can we move further? Write in chat box. Can we move? Okay. So okay. So let's come to this. What is ideal transformer? So ideal transformer is that in which no power loss is there. Okay. No copper loss is there. No hysteresis losses are there. There are different type of losses like hysteresis losses, core losses, different losses, copper losses. So we have to consider that there is no loss present in the transformer. That transformer is called ideal transformer. Okay. When you take ideal transformer, you know that there is a flux generation in the primary side. So all the flux generated across the primary side may be transferred. Okay. Because this is an ideal transformer, no losses are present in this transformer. That's why all the primary side flux is going to be linked with the secondary side. Okay. When all the flux is going to be linked with the secondary side, 100% efficiency will be achieved. Okay. So as you can see, no ohmic resistance will be present, no magnetic leakage flux is there, no power loss is there. Therefore, output must be equal to the input. Okay, 100% efficiency will be generated in ideal transformer. So, how to calculate this output? How to calculate this output? So, in the output side, we have used voltage as E2 and current as I2, and then we have to use the angle cos of phi. Okay. So the previous efficiency derivation, we have calculated this V2 into I2 into cos of phi. Okay. In the previous derivation. So in this derivation, we have assumed that this E2 is the EMF across this secondary side, I2 is the current across secondary side, and cos of phi is the angle across this load. Okay, we have to equate output and input side both. Okay, we have to equate. So when you equate these terms, the equal term they cancel out. So this cos phi is going to be cancel out, and P2 into I2 is equal to E1 into I1, and from here you can derive the equation. Okay, you can derive the equation using E2 is equal to I1 and E1 is equal to I2. So, but it says the number of the EMF generated across E2 depend upon I1. Okay, the EMF generated across E2 depend upon I1, and this I2 generated in the secondary side will depend upon E1. Okay, so when this EMF is generated across primary side, then this current will be dependent upon this EMF E1. Okay, understood? Any doubt till now? How we have calculated these equations? Write in chat box. Understood? Any doubt till now? Okay, so now we have to calculate a transformer ratio. Okay. So how to calculate this transformer ratio? This transformer ratio can be calculated by using this number of turns. Okay. So as you know that E2 is directly proportional to N2. Okay. E2 is directly proportional to N2. So this E2 will depend upon this number of turns. Okay, N2. So E2 is directly proportional to N2. and even, this is even. Even is directly proportional to this N1. Okay. So we know if these equations are directly proportional, then we can say that this voltage is equal to V2 and this voltage is equal to V1. So we have to put these values in this equation. So here is V2 upon V1 and E2 upon E1 is equal to N2 upon N1, and it is equal to I1 upon I2, and it is called as a transformer ratio. Okay. Any doubt till now how we have calculated this transformer ratio? Write in chat box. Write in chat box. Understood? Any doubt till now? Okay. So this is the transformer ratio. Now come to the next step. There is a step up transformer and there is a step down transformer. So what is the step up transformer? As you can see from this figure, in the primary side there is N1 type of winding. In the secondary side there is N2 type of winding. And you can see from here N2 winding is greater than N1 winding. Okay. So when this N2 winding is greater than this N1 winding, it is called a step-up transformer. Okay. So here, if we apply voltage like 12 volt, it can be increased up to 24 volt. This is called a step-up. Okay. Now come to this point. Here is step-down transformer. Here, primary side of the winding is N1. Okay. And secondary side of the winding are N2. So as you can see, N2 is greater than N1. Okay, then it is called a step down transformer. If you apply 230 volt right here, it can be reduced to 25 volt or 24 volt, 9 volt, 5 volt, as you wish. Okay, so you can change these voltages. These are called step up and step down transformers. So how you can find out which one is a step up and which one is step down? It depends on the number of turns. If your primary side number of turns are more and secondary side number of turns are less, it is called as step down transformer. If your secondary side number of turns are more and primary side number of turns are less, it is called step up transformer. Have you clear? Read out till now, write in chat box. Clear. Okay. Let's come to the next point. So how this transformer ratio or this EMF ratio can be calculated? How these ratios can be calculated and how this EMF equations will be calculated. So first of all, we have to draw the diagram of closed transformer, okay? Single phase transformer. So here we have drawn the diagram for single phase transformer. In this single phase transformer, we have used E1 the voltage across primary side, I1 is the current across primary side, N1 is the number of turn across primary side. When you pass this I1 current, some flux is going to be generated in this primary side winding. Okay, that flux can be linked toward the secondary side where this number of turns are N2, voltage is E2, and current is I2. Okay, so let's understand this phasor diagram first. This is an inductive circuit. Okay, when this inductive circuit is present, okay, so what happened? Im lag behind the voltage. Im is a current lag behind the voltage by 90 degree. In the previous lectures we have completed these topics in detail. Okay, in RL circuit, RC circuits, we have covered these topics in detail. Okay, so in early inductive circuit, this current lags behind the voltage by 90 degrees. So you can see from this diagram, here is the current and here is the voltage. This current lag behind this voltage by 90 degree. Okay, so from here, from the definition of RL circuits or this purely inductive circuit, you can draw the phasor diagram like this. Okay, whereas phi m flux is in phase with the phi m. We have seen in the resistive components. Okay, so this phi m is in the phase with this phi m. Okay, now E1 is the out of phase with the V1. So with respect to this V1, EMF is going to be generated E1, so which is out of phase with the voltage V1. Okay, so it is represented in downward. Why? Because it is out of phase with the V1. Understood how we have calculated this phasor diagram? Write in chat box. These questions will be asked in your examinations, that how phasor will be changed when you use inductive circuit, when you use capacitive circuit, when you use resistive circuits. Okay, write in chat box. Have you understood this? Any doubt till now? Clear? Okay, so now come to the next point, how to calculate this EMF equation. How to calculate this EMF equation. For calculation of these EMF equations, we have to calculate the sinusoidal waveform and we have to calculate this average rate of change of flux. Okay, so to calculate this average rate of change of flux, you have to consider the first half cycle. Why we have to consider the first half cycle? Why not complete cycle? As we have seen in the previous lectures, that if you consider the complete cycle, then what happens? These phases are equal and opposite with each other. They will cancel out, and in average, they will equal to 0. So average value for a complete cycle is equal to 0. Okay, so that's why we will consider only first half cycle of this complete cycle. Okay, for calculating the average, we have to consider the flux, this phi m of positive cycle and minus flux of the negative cycle. Then we have to divide it by 2. Why we have to divide it by 2? This complete cycle is represented by T. So how to calculate T? T is equal to 1 upon F. So time is equal to 1 upon frequency. Okay. So this complete cycle is T. If you cut from this half position, so what is this T? Right now it is 1 by 2 F. Okay. Because this is half portion. Okay. So that's why we are using this half right here, and we have to solve this equation, and we have to find out that this average rate change of flux for one half cycle is 4F m amperes per second. So this the unit is amperes per second. Understood? Write in chat box. Write in chat box. Understood? And we move further. Any doubt till now? Write in chat box. Write in chat box. Have you understood this concept? Okay. So most of the students saying they understood. Let's come to the next point. Okay. So for this sinusoidal waveform, we know the RMS, the ratio between RMS value and the average value is equal to the form factor. Okay. So we can find out the values for this RMS value. So this RMS value is equal to 1.11. So what is this 1.11? 1.11 is a form factor. Okay. Into average value. We have calculated the average value 4F into phi m. Okay. So we have to multiply these equations and the RMS value for EMF induced per turn is equal to 4.44 F into 5 volt. Okay, clear? Any doubt till now? Write in chat box. Any doubt till now? Write in chat box. How we have calculated this RMS value? Have you understood? Write in chat box. Okay, so RMS value for EMF induced in primary. So in the primary side, we are using this EMF as E1. Okay, so how to calculate this? You know the formula for this EMF is equal to EMF induced per turn multiplied by the number of primary turns. So we have calculated the EMF. The value for EMF is 4.44 F into 5M, and we have to multiply it by number of turns as N1. On the secondary side, we have to multiply it by number of turns N2. Okay? And we have to put all the values for this EMF induced per turn right here. Okay, so in this way we have calculated EMF across primary side and EMF across secondary side. Okay, write in chat box. Have you understood these equations? How we have calculated this EMF across primary and secondary? Okay, so okay, now so we have to calculate the ratio for this EMF. Okay, so output divided by output. So this is the secondary side EMF, and this is the primary side EMF. All the terms will be cancelled out. Okay, so this will cancel out, this will cancel out, this will cancel out. So values for E2 upon 1 is equal to N2 upon N1. It is represented by K. K is a transformer ratio. Okay, so we can use this for the maximum flux density. Okay, so how to calculate this maximum flux density? So this maximum flux density is calculated using Vm into air. Okay, so we have to put these values right here, and we have to calculate this EMF equations for primary and secondary winding.